starting the talk. Today we're having Yuri Levin here to give us a fun talk about black holes. Yuri is the group leader of compact object at CITA and the Flatiron Institute. Obviously, he's a friend of lots of people here, so probably people are more familiar with him. So I just quote some words from his website. Yuri works on several topics in the field of radical astrophysics. His main interests are neutron stars, especially magnetars and neutron stars in low-mass X-ray binaries, supermassive black holes, especially the Sagittarius A, and astrophysical gravitational waves. For his PhD at Caltech, he worked on the theory of thermal noise and on quantum non-demolition measurements for LIGO. He is continuing to work on the physics of LIGO with focus on thermal control of the LIGO test masses. So let's welcome Yuri.
Okay. So hi everyone. It's kind of an experimental talk. I think everybody in this audience was moved by LIGO's detection of black hole mergers in 2015.
Yes, 1/500
obviously LIGO will switch on for all three pretty soon. And there'll be more spectacular discoveries in this respect. I want to, in this talk, to take you a little bit beyond what is the standard astrophysics with binary black holes, and to talk about things which are a little bit on the edge of conventional astrophysics. So in particular, I want to discuss two topics. First one is gravitational wave memory from black hole mergers. I think there is a good possibility that gravitational wave memory will be measured by one or several of gravitational wave observatories. So I'll tell you what it is and tell you how we can measure it. And then I'll talk about something which is completely speculative but looks pretty beautiful. So it was fun to play with and continues to be fun, which is the new source of gravitational waves. These are little nets of black holes connected by cosmic strings and moving in interesting ways. So let's just remind you that black hole is the simplest object in the universe. It's described by only two numbers. At least astrophysical black holes are described by mass and spin. They have this structure. I presume this is completely familiar to most of you. Anyway, just briefly, you have horizon. Around the spinning black hole, you have ergosphere, where space light cones are inclined towards the motion of the black hole. Everything gets dragged in the same direction. This is the region where astrophysical black holes connect to the outside world, and they can exert energy, drive jets, etc. Now, if you are God and you want to make a simple object, obviously you make a puncturing space-time, and here is a black hole. Here is an object. Okay, give it a bit of spin. If you want a simple dynamical process, you make two punctures next to each other, and you watch how they move around each other, merge, and give off a burst of gravitational waves. So this is what LIGO has seen. It took us a while to calculate this and to figure out and build machines to measure it. But in fact, this is very simple. You've all seen movies. I won't play them. Let me just remind you that there are 5 black hole mergers which have been published by LIGO. The first one is GW150914. Many of these black holes are more massive than what was measured in the galaxy. So you can see in particular these 3 progenitors are more massive. There is a publication which is being prepared by LIGO Science Collaboration where they'll publish a full catalog. So these are not the only black holes that have been measured. There's a few more that will come out probably in the next several months. This is what the signal looks like. Just to remind you, you have several components of the signal. The first one is the in-spiral, where black holes circle around each other, lose energy by emitting gravitational waves. If you measure this in-spiral, you can infer various parameters like chirp mass, post-Newtonian coefficients. Mass ratios are a little bit harder. Spins are quite hard, but doable. Okay? Then there is merger. Merger is where the Hawking's theorem is enforced and the horizon area grows. And after the two black holes merge, you get a perturbed Kerr black hole, and the perturbation rings down in this phase. And of course, the ring down, if you measure it, tells you about the quasi-normal modes of the Kerr black hole. You can do seismology. You can probably give Kerr a Nobel Prize if you measure all of these modes very precisely, okay, and confirm Kerr metric. What I'm going to talk about today, at least in the first part of my talk, is the part of the waveform which is usually not plotted, which is the gravitational wave memory, as discussed by Dimitrios Christodoulou, a mathematician in Princeton. And what it says is that all the waveforms that you see are shifted up by a constant value at the end. And this is called the gravitational wave memory. And so I'll explain in a second why that is. This is exaggerated here by a factor of 4, just to be more visible on this waveform. So in reality, it's a little bit smaller. But it is present in all of the waveforms. It should be, in fact, when people plot waveforms, they should plot it, because it is an essential component, which is an essential feature of general relativity. Now, what is the origin of this memory? It's actually quite simple to explain. So suppose I have some cosmic explosion which sends out projectiles. Each of these projectiles is flying with a constant velocity. So if you now recall your first course in GR, and you know from this first course that the gravitational wave strain away from some distant source scales as the double derivative of the quadruple moment. Okay, so take a quadruple moment, double derivative, divide by the distance. This is your gravitational wave strain. Now, each of these bullets is flying with a constant velocity. That means that the quadruple moment of each of these bullets is a quadratic function with time, right? So that means that if you take a double derivative of a quadratic, you get a constant. So each of these bullets, as it flies, creates a constant contribution to this h. And that's a memory. So explosive events which send out projectiles, if these projectiles are not distributed isotropically, create memory, create a permanent distortion in the metric of space-time. Now, what Christodoulou realized, or at least to be more precise, what he calculated and what Kip Thorne realized the year after, is that you can substitute these projectiles, these bullets, with gravitational waves themselves. Okay, so gravitational waves are not just ripples propagating in space-times. They're ripples that carry energy and momentum that are propagating in space-time. So the gravitational waves, so think of these bullets as gravitons, which are flying away anisotropically from this merger. And gravitational waves themselves create in completely analogous way. They create kind of like a quadrupole moment which scales proportional to t squared. And so gravitational waves themselves create this constant contribution to the metric. So just to bring you into focus, suppose I have an event which emits gravitational waves like jets, up and down, and nothing sideways. Okay? So this event, if you're an observer located sideways, will create a permanent distortion at the observer, a permanent distortion of space-time. Any questions? Yes?
Yuri, why is it anisotropic?
Well, because if you have a merger of two black holes, gravitational waves are not emitted isotropically. There is more which is emitted along the direction perpendicular to the orbit of the merger.
So gives this rise to the gravitational wave kick?
Of course, memory is much larger than the kick. You know, the kick has relative amplitude of about 1 in 1,000. So yes, anisotropy also gives rise to the kick. But for example, you can have fully compensated 2 jets of gravitational waves, and they will not create a kick, but they'll create an anisotropy, they'll create a memory. So there's a nice calculation by Mark Favata, which kind of reinvigorated the subject, made it more appealing for gravitational wave astrophysicists. So this is what a comparison of a real calculation of conventional gravitational wave, so to speak, and gravitational wave with memory. And you see as the merger proceeds, you build up the memory component, and here it is in the red. This is what it looks like. And Favata argued, I mean, it's remarkable that this hasn't been noticed before, but he noticed that this component, okay, so remove the oscillating component, just leave the memory component, which is basically ramping up over the last few orbits. He noticed that this will be completely measurable in LISA, okay? So here is the 2 graphs from his series of papers that he published in 2008 to 2010. So this is kind of schematic, but this is the LISA noise curve, okay? This is the gravitational wave itself. This is the AC component, and this is the memory component. And you see that memory component, this is for mass of 2 inspiraling 10 to the 5, 2 times 10 to the 5 solar mass black holes inspiraling together. And you see that the memory component, the characteristic strain of it sticks out above the LISA noise.
What do you mean by DC components of constant? You mean you convert the step function?
Yeah. So see, it's kind of like a step function, even though it looks like it's doing it slowly. But remember, the time scale for these final oscillations is very short. So it ramps up over the last few oscillations. Yeah?
Is it always positive?
No. I mean, nothing is, it's gravitational wave, so it has quadrupolar. Any gravitational wave, if you rotate it by 90 degrees, changes sign. Right, so nothing is always positive. Okay, so here, so yeah, he plotted, and look, this is quite remarkable. So I think it's unfortunately cutting off at the low edge, but this is mass in solar masses, okay, the mass of merging black holes. And I think it's quite remarkable that for black holes, say, merging, well, the peak of black hole mergers occurs at redshift about 2. So for those black holes, merging black holes, it's like 1 million solar mass, give you memory signal which is of order, 7 or 8. So clearly detectable signal. For some reason, at least the people are not mentioning it very much, but I think this is quite remarkable and quite a remarkable component of that mission.
Is the time dependence the same? So like when you see this big supermassive black hole sweeping through the band,
yeah.
you see the memory also sort of like ramp up?
Yeah, the memory is ramping up. So this is, let me show you again. This is the Favata's plot. So memory is, as I explained, is proportional to is created by the flux, anisotropic flux of gravitational waves. So as this flux is ramping up, the memory signal accumulates, okay? So as soon as you stop the flux of gravitational waves, that's it. It remains at this level forever until the end of the universe.
There's a question, I have the same question. What happened to the oscillating component? Isn't it much stronger than this step function?
Sure, but it's dying. It doesn't last forever, right? The 2 black holes merge. You get distorted black hole. It makes a few oscillations, and then the distortions get carried away. And you're left with a pure black hole. Yes, that's right.
How do you attach the merger to a memory signal as well, I guess is maybe what I'm wondering.
This is it. This is the full waveform, okay? So you have oscillatory part and you have a slowly ramping up part. This is what happens.
That should just be a better coalescence as opposed to something right in where you see the coalescence.
Right, is that really true?
Say again?
What I said was it has to be super supermassives, you actually see the coalescence in the Lisa band, as opposed to something light, where you'd see them approaching each other in the Lisa band, and then they pass into the...
Yeah. These are for supermassive black holes. That's right.
So afterwards, your length between the things is just slightly shorter.
It's slightly shorter, right? So Martin has a good description, right? If you take a cloud of particles, I'll show similar pictures. But if you take a cloud of particles, and you have a gravitational wave, merger of black hole, the distance, this cloud will oscillate. Cloud is, if you measure distances, right? If you try to make a map, this cloud will oscillate, and then it will remain slightly distorted. Okay.
It's a direct analog of E and M too, but now you're dealing with the dipole moment rather than the
Yes, probably.
What's the self-gravity of the field that's causing it to be EM?
So they're both carrying energy.
Yeah.
So the energy leaves the sphere.
Okay, come on, guys, come on. Let's get on with it. Right. So anyway, so I think it's remarkable that it's detectable, and for some reason, at least the people should talk more about this. But the interesting question: what about other observatories, right? What about LIGO, and what about pulsar timing arrays? And I will try to argue with you that LIGO is kind of doable. I'm getting a little bit more skeptical about it, actually. I'll explain why. Pulsar timing arrays, the signal will be beautiful, but you have to wait for a long time. Okay, so with LIGO, and this comes back to the illustration that Martin was alluding to. This is Polaski Slide, where he said, okay, this is what it is, LIGO without memory, and this is what it is with memory, right? So here it is. And even better analogy is this one. Without and with. And of course, this is totally wrong. Okay, this is wrong. This creates confusion, because in fact, this object has internal forces which are keeping its shape. Okay, so, but if this was a cloud of particles, right, which are not interacting with each other, then this cloud would be left distorted. So how big is the effect? It's pretty big. It's about 1/20th. Okay, so this is backwards. Okay, the memory strain divided by oscillatory strain is about 1/20th. It doesn't depend on how far you are away from the merger, so it's always like this. And so you're going to ask, well, is this really detectable? Okay, first order of magnitude, the merger GW150914 had signal to noise of like 30. Okay, so why not? Maybe it's marginally detectable there, but no, it's not.
Principle, it would integrate way, way, way longer, right? If you really were totally stable, you would actually be way more sensitive to that memory offset than to your oscillations, because you just integrate for a year before and a year after, and you say, hey, there's an offset.
No, not right. Not right.
They're tied down to the ground.
Yeah, no.
That tied out the ground, exactly.
Time constant in there.
Exactly. So, and this is why, Kip Thorne, you don't slowly build up his distortion, right? You have to, you're sensitive to the kick. You're sensitive to the memory kick. So, for example, for LIGO, so this thing that Polaski did, it's also misleading, because of course LIGO doesn't do that. LIGO is attached to the ground, but it's trying to do it. Okay, it's giving it a push, and because this push is time dependent. Yes, it will start swinging. This thing will start swinging, and that is what you're detecting. You're detecting this push, right? And LIGO is sensitive. The frequency of sensitivity for LIGO is above 10 Hertz. So you're never sensitive in LIGO to the DC part. You're only sensitive to the tail part of the push. For LISA, in principle, you don't have that problem. Yes. Okay, so it's about 1/20th. Now, so it turns out that a single event, LIGO will not see, even when it reaches the design sensitivity. Okay, so all the numbers that I'll give in a second, they are numbers describing the optimistic, I think, case that LIGO reaches design sensitivity, advanced LIGO reaches design sensitivity. It's not possible even if LIGO reaches design sensitivity to detect individual memory events. It's too weak. But what you can do is you can ask a question. Suppose I have two models of the universe. One model of the universe where Christodoulou is wrong and he made a mistake and there is no memory. And another model of the universe where Christodoulou is right and there is memory. Then you can look at ensembles, okay? And you can ask a question, which model of the universe describes an ensemble of mergers better, the one with memory and the one without memory. And if you have the same weak signal, which is present in all of your merger events, then you'll be able to, add them coherently, provided that you can predict, in each merger event what the expected memory signal is. So the proposal is, instead of trying to look for individual memory signals in this burst, you are measuring, for each of this signal, for each of the merger, you know exactly when it arrives. You can subtract oscillatory components, search for memory, and you can then design optimal statistic for adding the weak signals for each merger in an ensemble fashion. Yes?
I have a question about this, which will give away that I don't know a lot about gravitational waves. Because that memory can be positive or negative,
Yes.
is it possible to see, just with our detectors here under the way the orientation of everything in space, that you could get both positive and negative signals and still see it, say with LIGO or LISA?
That's an excellent question. And it leads me into a problem with this method. But let me I'll come back to it in one slide. But let me just for now assume that for each merger that happens in the sky, strong merger like GW15 or 914, let me for the moment assume that I measure the parameters of that merger so precisely that I can predict, using general relativity, exactly what the expected contribution from memory is. Okay? Let me make this assumption. And then I have a well-defined model for what the expected contribution of memory is. I will show why this assumption is a tricky one in a second. So if you make this assumption, then you can add the statistics from many mergers, and then you slowly, event after event, you will build up evidence for memory. You will build up signal to noise for memory. And you need something like 35 loudish black hole observations to build up conclusive evidence for presence of gravitational wave memory. What do I mean by loudish? I mean the events which are the same as GW15 or 914, the very first measured merger, if LIGO is at the level of advanced, if advanced LIGO reaches its target sensitivity. Okay? So that's how much you need. However, there is a subtlety, and this subtlety is related to the sign of memory, actually. It's a little bit tricky, but if I have a binary in the sky, this is my binary, and it produces some gravitational wave, okay? And then I take this binary in the sky and I rotate it by 90 degrees about a line which connects me to a binary. The sign of gravitational wave will flip. This is just simply because gravitational wave has a quadrupolar, it's a quadrupolar pattern. If after doing this, I take the binary in its own plane and I rotate it by 90 degrees, okay, the whole orbit, the whole in spiral, this will flip the quadrupolar component of the in spiral, give it another negative sign. So I will come back to the original waveform for the quadrupolar component. However, my memory will flip the sign after these two transformations. That means that I have no way, at least in the quadrupolar approximation, I have no way of predicting the sign of the memory from the oscillatory waveform.
Well, the way you measure them, if you have enough LIGOs, you get to measure the first step.
This is a symmetry. Okay, this is an exact symmetry. Okay, H22. These two angles about which I flip. So this gives you exactly the same oscillatory H22 waveform, but the memory waveform flips. This is an exact mathematical transform. This is a fact. Okay, it doesn't depend on any approximations. So if you want to measure the sign of memory, you have to get some information about this higher order modes that you excite during the merger. Now, luckily, GW150914 was so strong that if LIGO was at the level of its design sensitivity, you would get some information about this higher order modes. And higher order modes can help you break this degeneracy, right? So if you have higher order modes, you can get some information about which of this orientation it is, and you can make some statistical statement about which sign of memory is more likely, whether it's plus or minus. Typically, you cannot determine it exactly, so I summarize this state of affairs like this. So you cannot predict precisely the sign of memory, but you can give strong statistical preference, right, from the information about the higher order modes. And this is enough to start helping building you the statistics from multiple mergers.
In principle, if you never knew the sign, you still have a random walk. So you just need 1600.
That's right. You would need, that's exactly right, 1600, yes. If you had 1600 events, then you would be okay. But that's a bit, yeah.
Would it be fair to just go through all the permutations of signs with your small number of events and see if you ever got a signal?
So that would result in what Martin is saying. You would lose the coherence of this thing.
No, but eventually you might guess the right combination. Each one could be plus or minus. You just do all the permutations.
Yes, but in the process you are, you're reducing this. You have so many trials that you're reducing the evidence for what you're trying to prove. So we have done this exercise, and no, it doesn't. It's exactly like what Martin is saying. You need 1600 trials. But if you use the higher mode information statistically, it turns out that 40 GW150914 type events in advanced LIGO target sensitivity is enough to accumulate substantial evidence for memory. Now, why am I skeptical about this, or getting skeptical, is because LIGO doesn't seem to be able to reach its design sensitivity. And it's especially important for this experiment. It's especially important at low frequencies. Okay, and LIGO has this low frequency noise that they haven't been able to control. Okay, so for high frequencies, they're okay. For low frequencies, they're having problems. So at the moment, I'm a little bit, at first I was very optimistic that LIGO will be able to do it before LISA, right? LISA is like 2034. Okay, this is the date when it flies. I was sure LIGO will do it first, but now I'm not so sure anymore.
Is it clear that the low frequency noise in LIGO is noise?
No. Well, is it clear that it's a Gaussian noise? I don't.
No, I mean terrestrial noise.
Oh, could it be something else? Yeah, because, well.
Sorry, that's sort of.
Yeah, no, it's a question that bugged me too. Like, I think they think most of it's terrestrial. Okay, now PTAs, of course, beautiful long-term experiment using pulsars. You all probably know about it. The idea is that you have these excellent Einstein clocks in the galaxy that are being monitored from Earth. And the gravitational waves, when they come, they distort the regularity of the arriving pulses. So you can use this information. So this is just mathematics. If you have the millisecond pulsar here, the Earth here, gravitational wave propagating in this direction, it gives you the frequency shift of arriving pulses, which are given by this expression. Okay, this is important. Please pay attention. Delta nu over nu is some geometric factor, okay, multiplied by the difference between gravitational wave intensities on Earth and at the pulsar, okay? On Earth, evaluated now, at the pulsar, evaluated at retarded time. So there are two components, two contributions to this frequency shift. Now, this contribution, arrival on Earth now, is correlated between all the pulsars, okay? So a gravitational wave arriving from random direction through this term will create the correlated changes of frequencies of all radio pulses in the sky. And we can show that if we have a burst with memory, it will create a frequency jump. Okay? So it will look like this. This is simulated data from Park's pulsar timing array. But all of these frequencies, this is a time of arrival. So the slope of this time of arrival as a function of time tells you about the frequency of the pulses. So if you see a jump and slope, that means that the frequency, observed frequency of the pulsar changed. So all of these frequencies will change at the same time. Okay, this is a prediction for what the burst with memory will look like. So if you are watching all the pulses simultaneously, okay, and I'm saying there will be a burst with memory coming from that direction with this amplitude, with this polarization, I can predict exactly by how much all the frequencies of all the pulses should jump at the same time. Okay, so it's quite a remarkable signal if you see it. And people have looked for it. So this was predicted by 3 groups independently, including my PhD, ex-PhD student, and myself. And people have looked for it. So PPTA, Park's pulsar timing array, has looked for it. Nanograph has looked for it. And they didn't find anything. And it's not surprising that they didn't find anything, because the event rate for major, and I'm talking like 10 to the 8th lower mass binary black holes, merging, within redshift 1 or so, in the past light cone of pulsar timing array experiment is very low, unfortunately. So probably you would have to, so of course the estimates of this vary wildly. We don't really know the merger rate. We don't really have an easy time projecting of how well SKA will do when it starts timing pulsars. But roughly the numbers are that you would probably have to wait for 30 years or so when SKA comes online and when it starts timing millisecond pulses really well. So it's still within my lifetime. I fully intend to, see a burst of memory using Park's pulsar timing array, but I don't know if I'll be very active in doing research at that time. So maybe it's like descendants or whatever. So I think it will be seen, but exactly when is less clear. So okay, I would like to make conclusions for this part of the talk. So I want to say that gravitational wave memory is one of the, people often ask me, okay, this is all cute, but what is it good for? You can't use it to measure something else. It's just a fundamental effect which is predicted by general relativity. It's very non-trivial intuitively, and I think it would be good to measure it. And I think Lisa will measure it if Lisa flies. Advanced LIGO will be able to accumulate evidence from multiple events if it reaches target sensitivity.
Isn't it telling you an integral of things that happened that weren't in your line of sight? So in some sense it is telling you something about the waveforms you didn't already know.
Oh yeah, like I said, in principle the main emission of gravitational waves can be completely sideways. So for example, if you have a cosmic string, which I'll talk about in a second, cosmic strings emit gravitational waves from cusps in particular, and this is a very strongly directed emission, okay? So if you're outside of this very narrow cone of gravitational waves which comes from a cusp, you will never observe the direct gravitational wave, but you can see the memory signal from it. So there are examples where you wouldn't, you wouldn't see any oscillatory thing, but you would see a memory thing. Okay, and then PTAs, pulsar timing arrays, are sensitive to bursts with memory, but I think we have to be quite lucky, or at least patient, on a generational timescale. Yes?
Does the memory effect contribute to the background? You have all these memory effects going all over the place.
Yeah, it does. But I think it's a small contribution. I think people have tried to estimate it and haven't published it because it's not very strong contribution to the background.
So what's the relationship between EMS transformations and memory?
I don't know. People say there is some. I take it that.
It sounds similar, but I'm
Yeah.
not quite sure.
I take it it's related to. It's related to transformations of black hole spacetimes, which also give you solutions of GR, because memory is kind of like a constant distortion, which came out of nowhere. So they call it soft hair. I don't know. Yeah, for some reason I should say that many high energy physics people, they care about this memory effect and think it's important.
Well, the interesting question if you could have some modification of Einstein's gravity, which in astrophysical context wouldn't be distinguishable, but somehow makes a different prediction. I haven't heard of such a goal.
Is it at all motivated to consider other theories of gravity other than Einstein's relativity? Yeah. Okay, I agree. I want to move on to a different subject, which is much more speculative and probably will never be measured. But I want to talk about this scenarios of early universe where you have cosmic strings and also primordial black holes. So that means that these scenarios have a probability of 1/4 of being right. Anyway, so it's a joint work with Alex Vilenkin and Andrei Gruzinov, and we think it's a new class of scenarios for early universe dynamics, but I say new class is because we don't really understand very well the behavior of what we are proposing. So maybe with further study, this whole class will collapse to like 2 models or something like this. And I think it's also a new class of gravitational wave sources, which I drew schematically here, which are these like small nets of black holes connected by cosmic strings. And they radiate gravitational waves in interesting ways. So first of all, I don't think cosmic strings is like mainstream astrophysics. Perhaps not very, I learned about them myself with a great deal of pleasure. And I think they're worth keeping in mind in lieu of what I said in the beginning is like what else is out there? Is there anything outside of mainstream astrophysics that may possibly be detectable? So what is interesting to me is that, first of all, from the physics point of view, they're absolutely fundamental objects in the same way as particles are fundamental. So particles, in special relativity, they trace out trajectories which minimize interval in space-time. Strings, they trace out trajectories that minimize area in space-time. So the kinematic description is extremely compact and simple, and it's known as Nambu-Goto action. Okay, so this is, at least for a theoretical physicist, this is a very appealing way of describing motion. The second thing about strings is that their tension is the same as their mass density. Tension is, of course, energy divided by length, but both energy and length, they have the same units in general relativity. Okay, so it's essentially a dimensionless number. This tensionless is a dimensionless number in units where G equals C and equals 1. So that means that strings are characterized by this dimensionless tension, and that's it. Okay, well, to the first order approximation. There is nothing else in sort of macroscopic description of the strings. Now you ask, what is this tension? What is known about it? And variety, the reason why this whole field has received so much attention early is because strings arrive naturally in early universe cosmologies. And the numbers for this tension can be anywhere between 10 to the minus 6 and 10 to the minus 32. So there's a wide range of scales which can give you cosmic strings, which is consistent with our current understanding of particle physics. You ask me, what about observational constraints? How strong are the observational constraints on this region? The observational constraints is that this tension is less than 10 to the minus 11. So you only you constrain a small portion on logarithmic scales of this, what these cosmic strings are. Okay, where does this constraint come from? It comes from pulsar timing arrays. I'll explain in a second. The third feature of strings is very simple. So each of the strings is carrying magnetic type field. And when these two strings intersect, they reconnect. And they reconnect in such a way that the direction of the magnetic field is continuous. Okay? The fourth fact that I want you to keep in mind is that if you have a loop of a string, it oscillates completely periodically in the frame of reference of its center of mass. And the period of oscillation is the length of the loop divided by the speed of light. Okay. So now, in principle, I told you enough. I told you all the ingredients to model the string network. Right? In principle, if you are smart enough, you listen to these 4 rules, and you can go away and you can program it, and you can derive the evolution of the string network. Okay? So people have done that. And the answer is as follows. Okay? Suppose I have a universe which is expanding according to some normal cosmological Friedman universe. And I start with, when I form strings, I have like several strings per Hubble volume, and I let them evolve according to the equations of motions in the expanding universe, and according to these rules that the strings, when they intersect, they reconnect. And also I should add that these loops, when they oscillate, they emit gravitational waves, so they shrink in length due to the emission of gravitational waves. So the answer is that this network, the string network, evolves in a similar way. So in each Hubble volume, you have several long strings, okay? And also you have much more length in these small loops, okay? And the people who are working in this field, they have been fighting about what is the distribution of sizes of these loops. This is one of the main issues that they're trying to solve theoretically. And it's these loops which give you gravitational waves. It's these loops which are responsible for particle production, string cosmologies, etc. So how are these loops formed? Very simple. When a string self-intersects, part of it gets pinched off, and what's left is a string with propagating kinks and stuff like this. Okay, so let me just mention a little bit more about this scaling evolution. Okay, so the reason I'm showing this is the result of a modern simulation of such system, which has, in yellow, it has long strings, and in red it has string loops. And this scenario is so well defined that people think that they can make well-defined predictions for what the distribution of these loops is. And then they can make predictions for gravitational waves that these oscillating loops will produce. You can use pulse timing arrays to look for these gravitational waves and to place bounds. Okay, and the current bound implies G mu, which is less than 10 to the minus 11. Okay? So
the numbers don't depend on the mass density in the strings.
This is...
The fact that you have 10 long strings per horizon.
Yes, that's right. That's independent. So let me just summarize. I note your question, but let me just summarize. Okay, maybe you haven't followed everything I said, but in summary, there is a system, of long string-like objects, strings, which follow easy rules, easy equations of motion, easy prescriptions for reconnection, okay, easy understanding of how they emit gravitational waves. And even though computationally it's difficult to simulate how the system evolves, but conceptually it's easy, okay?
Until you want to put in the radiation reaction.
But even, well, okay, but radiation reaction from gravitational waves, that's completely understood, at least as a matter of principle.
But to follow all the little loops. Are they following all the little loops and the self-fragmentation and so on?
But it is not conceptual. I'm saying conceptually it's a very simple system. How it's done computationally is a different matter. Okay, computationally it's a hard problem.
The number of
But
loops must depend on the mass density then, because that depends on how fast they shrink.
well, it seems that this result, so the result, like I say, is that there is 10 long strings per Hubble volume. That seems to be robust. Okay, and this is crucially important for what I'm going to say.
Loops can depend on the mass scale because
But the size.
reaction helps determine the size of the loops that split off.
That's right. I agree with that. Yes, the size of the loops. Yes, and this is the main fights are about the size of these loops. So this bound should be taken with some grain of salt, but at least with improved calculation, it's clear that you can get control. The theory, I would say, is not completely under control from the computational point of view, but it's not too far from being under control. Okay, and there are some people that believe it's under control. And I think it's quite an achievement. Okay, you have some simple system, simple prescription for how the system evolves, and you have some results and have some observational bounds. So, kudos to those people, right?
So which do you form first, the black holes or the strings?
Wait a second. You form the strings first.
What do you have?
Oh, a second, it's coming. Okay. Now, the strings is one of the simplest possible ways of breaking symmetry. There can be more complicated things that happen, okay? So more complicated examples of symmetry breaking is when you first form monopoles, okay? So you have monopoles and anti-monopoles, and then you have a symmetry breaking which makes strings. So then you have this monopoles which this magnetic flux gets confined to strings, and you have chains which consist of monopoles, anti-monopoles, etc. So this is important because your string network is now can be populated by magnetic charges. So, and the dynamics of this string network can be considerably more complicated. Okay. Now, but I'm just saying that simple extension of simple symmetry breakings can give you more complex structures. Okay. Now, about primordial black holes. I think strings are pretty well motivated. From the first principles, in terms of particle physics, whether they exist or not is less clear, but at least there is a clear motivation why people started talking about strings, right? That you have symmetry breaking. We know that we have symmetry breaking in the universe, etc. Okay? And that's why sensible astrophysicists like Chris Thompson and Jerry Ostriker, spent years thinking about cosmic strings. Okay, this is not just some wishful thinking. I think primordial black holes is pretty close to wishful thinking. This is my this is my personal opinion. But many people like to think about primordial black holes. I think, in particular, after Hawking came up with his effect of Hawking radiation, black hole evaporation, primordial black hole is essentially the only population in black holes that can be subject to that effect. Okay, so if you want Hawking radiation to happen in the universe, you have to invoke primordial black holes. My take on it is, okay, we have simple inflation, which gives nearly flat spectrum, delta rho over rho. We know it's less than 1 from CMB observations. Okay, now this is tested by CMB for L's of order of several thousands, right? It's tested by large-scale structures and mass scales, which are greater than about 10 to the 13 solar masses. But I would say we have no constraints, and please correct me if I'm wrong, but we have no constraints on this delta rho over rho on smaller scales. So in principle, at least there is freedom to consider different delta rhos over rhos. I wouldn't say there is, at least to my mind, there is no particularly compelling motivation except for wishful thinking, but at least observationally, it's not illogical to consider this possibility. If you consider this possibility, then people came up with many versions of inflation, etc., which give you delta rho over rho on an array of small scales. Okay? And if you have delta rho over rho, which is of order of 0.1 on small scales, then some regions will have delta rho over rho of order 1, and then those regions will collapse and form black holes. Okay, so these are primordial black holes. The mass of the black holes is exactly equal to the age at which they collapse. Okay, so it really depends on unknown things. But astrophysical black holes, astrophysically interesting primordial black holes that can do things for you, typically have masses which are such that you form them after you form strings. So again, this is driven not by understanding of.
So you're interested in astrophysical black holes.
If you want these black holes to do something, okay, then they form after strings. Okay, and why have people wanted these black holes? People wanted these black holes to make dark matter. Okay, that's one idea. You can use these black holes. Why invoke some particles? Why don't we have primordial black holes as dark matter? That's one possibility. Another possibility is people wanted these primordial black holes to become seeds for supermassive black holes in galactic centers. Because, some people, when they hear that it's not so easy to form them using normal astrophysical means, they immediately jump to the conclusion, let's do it using primordial black holes. So people have all kinds of fantasies of what they could use them for. Let me just skip, because I'm running out of time. Let me just say two things, okay? First of all, I want to say that because the size of this forming black holes is comparable to Hubble horizon, each of this primordial black hole, when it's born, will get threaded by several long strings. Okay? It's interesting to think of how this network will evolve. Let me just tell you that typically the way this network evolves, okay, well, these black holes can get pinched off. There are all kinds of things, all kinds of arguments we can go through. The main thing is that as the universe expands, the strings that stretch between the black holes will become straight. This is the first thing that happens. Remember, you expand by many orders of magnitude. So you will form kind of a lattice work of these black holes and strings connecting them. And then these black holes will feel the pull of the strings, and they'll start moving. And then this lattice will begin fragmenting. As these black holes move, distances of order of the lattice separation distance, this whole lattice work will start fragmenting. Let me omit the details, and let's just think about what are the possible fragments that come out of this lattice. And these are examples of possible fragments. So you can have binaries which are connected by pairs of strings. You can have triples. So in these examples, these black holes are connected by, these black holes are magnetically charged, so this is only viable if we have those necklaces that I showed you. In these examples, if you have a triple here, you know, these three black holes are connected by ordinary strings without necklaces, and this is a stable configuration. So this triple can live and move without these strings, you know, reconnecting. Okay, so Nathan and Simon had a workshop on triples at Flatiron Institute, and the dynamics of these triples is very different from the dynamics of other triples. Important thing is that all of these little nets, they radiate gravitational waves, and they shrink exponentially. Okay, they shrink exponentially with this time scale. So it's this time scale for reasonable tensions of order 10 to the minus 11 and reasonable masses of these black holes of order of solar mass. This time scale is of less than the age of the universe. Another way of phrasing this is that the time scale for the shrinking of a net like this is the age of the universe multiplied by the tension in these units multiplied by the mass of the black hole in units of 100 solar masses. In other words, if you have certain tension, it will preferentially drive mergers of black holes of certain mass scales. So for tensions of order of 10 to the minus 10, you get at current epoch mergers of black holes of order of 100 solar masses. So this is to tell you that even though I told you some crazy story, but this crazy story at least creates mergers within observable, for reasonable parameters, it creates mergers of black holes within observable gravitational wave bands. You can actually go and look for them. And now it's just the end of my talk. You're all tired, so I'll show you some movies. This is a movie of a triple, like that. Black holes connected by strings. This triple is, unlike Simon's triple, this triple is completely stable. It's chaotic, so this black holes will be brought together by give bursts of.
What's the ratio of the neutral gravitational force of the black holes and the tension force?
So here it's assumed it's all tension, so it all depends on which distance you started, obviously. But I think your question is a very good one also, because what I think will happen is that even if the separations are large, the chaotic dynamics will be such that randomly these pairs of black holes will be brought together and give off, feel each other's gravity, give off bursts of gravitational waves. So this is something that we haven't yet calculated through, but it may be that most of the energy is actually lost in short bursts of gravitational waves because of chaos.
So if I just put it might be useful to put in some numbers. So we've got G mu of 10 minus 10.
Yeah.
When the mass unit length is 10 to the 8, as I recall, 10 to the 8 kilograms per centimeter. So the energy unit length is 10 to 21 times that, so that's 10 to 39. The force is 10 to 39. And acting on a mass, say, of 100 solar masses, that's 10 to 35 grams.
Yeah.
And the acceleration is 10 to 4. So the black hole is being accelerated by this little string, this microscopic string, with an acceleration of, isn't that amazing?
Yeah.
That's cool.
Yeah, it is cool. It is cool. This is the only reason to even tell you about this, is because it's a really cool thing, if it exists. So I want to show you, now it's quadruple, just for fun, because of course, why stop at the triples? You can have 4 black holes which are connected by strings.
But those aren't intersecting strings?
Yeah, well, I don't know. I don't know if the configurations which are non-intersecting exist.
You have to check that.
I haven't checked that, no. my hypothesis is that no. My hypothesis is it's only triples that are stable. Okay, so, and this is an interesting thing, okay? This is a loop which is pinned onto the black hole, because of course, like I said, you can chop off pieces of string which are attached to loops. And it's an open question whether non-self-intersecting loops pinned to the black holes exist. We found one solution, but it's, we don't know how generic this solution is. So this is just a movie of how a loop into a black hole moves. All right.
So you pin a loop, and then you claim that it's stable to a pin radiation? No, it's not doing that.
No, so the question is, okay, you take a cosmic string loop, and you hold one of its points. Okay, this is what it means to be pinned to a black hole in real terms, because black holes are very small compared to the size of the loop. And then you let the loop move. And you ask the question, can a loop move in such a way that it will not self-intersect anywhere? And if you just try doing it, try different things, it always self-intersects. Okay, but Andrei Gruzino found one example where it doesn't. Okay, one example he found, just analytically. So then the question is, if you start with some loop and you let it self-intersect multiple times, will it find some stable configuration, or will it actually always be self-intersecting until it, so generically we don't know what happens, as a general rule. Okay, so, sorry, I'm at the end. I'm sorry guys, I'm running over time. But anyway, so these are new sources of gravitational waves, however crazy. But it drives black holes to mergers, so they will be seen as conventional, probably as conventional mergers. If you have a loop which is attached to a primordial black hole, these primordial black holes get pulled into galaxies. Okay, so in principle, this could be a way to bring cosmic string loops into galaxies. It could be fun to have them in galaxies rather than somewhere outside of galaxies. If you believe crazy people that want to make use primordial black holes as seeds for galactic nuclei, and these seeds then get hooked on some long strings, and these heavy black holes get brought into centers of galaxy, okay? And then there is a long string which is attached to them. It will stretch to the next nucleus, okay? So you have like nuclei of galaxies which I can, huh? It depends on the tension. It could not be, if it's strong tension, they will get pulled out. But if the tension is weak, they'll stay. And like I said, there's enough parameter space that the tension is weak. So then you'll have like a telegraphic network of supermassive black holes, connected by cosmic strings. And if this, if these cosmic strings are superconducting, right, they'll light up as bright radio filaments. I'll show you a picture. Okay, so here is a picture. Okay, this is not my paper, right? It's a paper by Mark Morris, who is a serious, observer looking at the galactic center. And he says we consider the possibility that Sagittarius A star is a manifestation of low mass density cosmic string that has become anchored to the black hole. Okay.
This is why this has a bad reputation.
This is clearly wrong. Okay, this hypothesis is, so like, you have to learn, even within this crazy speculative work, you have to learn how to tell right from wrong. So what Morris is arguing is that here is Sagittarius A star, okay, and here is the filament, the bright radio filament. I'm tracing it out. And he says the most, well, one of, he is so puzzled by it that he comes up with this explanation. So that it's a superconducting cosmic string. So I think this is wrong, but it's a nice exercise for some student class to criticize this hypothesis and to. I'm finished.